Okay, thanks again, Vince. As per the preamble and the agenda, the focus of this discussion is going to be not about typical H2S or CO2 type related corrosion. That's normally the topic of discussion in oil and gas applications. The focus here is going to be about dissolved oxygen and the effects of high TDS, high salinity brines, and their effect on corrosion. Again, as the industry keeps going towards more water recycle, water reuse, the handling of those high salinity fluids is going to become just increasing. So there's going to be more water processed through equipment, and that high salinity water is going to be pumped down. It's going to get oxygenated inevitably when it comes to the surface, and it's going to be pumped back down whole, whether it be in another stimulation or water flood or whatnot. So I'm going to really focus on those two things, dissolved oxygen and high TDS. Obviously, effects of things like pH, temperature, flow rate, pressure, and abrasion. There's still factors that affect corrosion, but I'm not going to really touch too much upon those today. Just invariably, pH, when we're talking about mild steel, I didn't put it in this collection of slides here, but if you've never seen the chart, you can look it up quickly online. Typically for mild steel, you're going to see from low pH down to about 8.5, and then start to go back up a little bit in the 9.5 to 10 range. You get minimal corrosion between that, say, 7.8 to 8.8 range, so which is usually outside the range of what we see in most produced water, most applications in oil and gas. So that's the effect of pH in a nutshell, very high level. Temperature, the rule of thumb, for every 10 degrees rise in centigrade or Celsius, corrosion rates can potentially double or do double. So that has to be kept in mind, especially if you're looking at going into various shale plays where you're dealing with higher temperatures. Flow rate from a pure, the ability to keep corrosion inhibitory films towards the surface, flow rate will affect that. Pressure, which determines how much dissolved CO2 and H2S you can have. Again, we're not going to get really into today. Abrasion effects, well, if it's on a frac job and you've got several million pounds of sand going through it, that's a whole other world. And again, I'm not going to get into that today, but it is another factor which contributes to corrosion altogether. So applications which are susceptible to oxygen and high TDS corrosion that presumably people in the group here are familiar with, obviously frac or any stimulation work. So even if you're fracking with fresh water, that fresh water is going to have dissolved oxygen in it. Okay, so it's not something that you can just completely overlook and say, I don't have anything to worry about. Coiled tubing work, drill outs, it's the same thing. Even if you're using fresh water, that water is going to be oxygenated. And on the slide here, that will talk more about oxygen. Drilling fluids, again, typically oxygenated fluids. I'll speak less about production tubulars. You're going to have typically oxygen-free fluid coming up through those, so that's going to be more high TDS effect. Gas, I know that there is oil production on the Utica side, and mostly for this region we're talking about gas, and we're talking about transmission lines. We're going to be looking at high TDS brine, but also possibility for oxygen inclusion in the small aqueous portion of the pipelines. And then produced water storage tanks, which is going to be more of a factor when we look at keeping that produced water for reuse and recycle. So oxygen corrosion, and I've ripped off a nice quote I found going through some information. So just read it. I'll read it out there. So there is no corrosion mechanism more damaging on a concentration basis than oxygen. And I had never seen this slide before, but I thought it was quite dramatic when you look at 8 ppm of dissolved oxygen gives you a corrosion rate of over 20 on this relative scale. you have 100 times more H2S and 50 times more CO2. And that small amount of oxygen outweighs those dramatic concentration differences. So this chart was really like, wow, never knew the difference was that dramatic. And as a rule of thumb, the colder the water, the higher the oxygen solubility. So when you're fracking in the wintertime, even with fresh water, you're going to be probably close to oxygen saturation. Even in the summertime, if the water's up around 75, 80 degrees, you're still probably talking about 3 ppm oxygen in that water. More towards the high TDS and chloride corrosion. So metal surfaces are never perfect, despite what they look like to the naked eye, being nice and smooth, etc. And so the high chloride corrosion, high TDS corrosion is really going to be an effect at these grains and grain boundaries, and that's where it'll set up anionic and cathodic sites. And just the fact that you've got that much stronger of an electrolyte and a conducting fluid, it really just enhances the galvanic cells in that form. So how do we inhibit corrosion in high salinity and high oxygen containing environments? The traditional imidazzling clot-type chemistry normally doesn't work well on its own, because usually those chemistries are only used alongside oxygen scavengers. Their film formation is primarily based on there being no oxygen present. Now in our applications, things like frac or coil tubing, etc., the use of oxygen scavengers is somewhere between impractical and just not really economically viable. Because of the volumes of water we'd be treating, you would have to add so much oxygen scavenger, even the cheapest ammonium bisulfite type oxygen scavenger, you would have to add hordes and hordes of it. And then on the flip side, you're also contributing sulfate ion if you're hoping to do it cheaply. And sulfate ion, I've always advocated against adding sulfate ion wherever you possibly can, because it does two things. It gives you a scaling counter ion if you have barium or strontium, or even calcium. And secondly, it gives a food source for sulfate-producing bacteria. So if I have a choice between adding sulfate and not adding sulfate, I'm going to choose not to add sulfate. So other requirements for the corrosion inhibitors, as mentioned with the scale products earlier on, obviously they need to be compatible with the other fluid additives and compatible in the brine itself. Usually a big challenge with the imidazzling clot-type chemistries is that they are all cationic. And so getting those to be compatible, now they're at low dose rates, they're very compatible. Obviously they're water dispersible, water soluble, etc. But in, let's say, close proximity or high concentrations to anionic compounds such as scale inhibitors and friction reducers, they don't like each other. So we could actually get interaction between the two. And when I spoke earlier of the example of the scale inhibitor winning out on its compatibility, that was one of the key features of that product, was that it was compatible with the cationic corrosion inhibitor at very high concentrations. So keeping the chemistry compatibility and also the brine constituents. Again, with high salinity fluids, a lot of times those waters of hydration are used to keep the other ions in solution, the sodiums, the chlorides, whatever calcium, barium, strontium, sulfates, etc. may already be there. And so to put other chemistry into that solution, you need free waters of hydration that can solvate your inhibitor. So, and a lot of times calcium again can be an issue. You can form calcium salts of various inhibitors. Because of the large water volumes we're dealing with for something like a frac or coil tubing drill out, or even produced fluids and gas transfer lines, we need something that's going to work at very low dose levels. And finally, preferably something that will be solely active in the aqueous phase, which is where these corrosion mechanisms are occurring. The clot-type chemistry, one of its attributes for use in pipelines, for both gas and oil, is that it can actually straddle between the hydrocarbon phase and the aqueous phase. So that actually gives you protection throughout the pipeline. In this application, when we're talking about oxygen and high TDS, we're really focused on the aqueous phase. So just some examples of how corrosive fresh water can be. Picture turned out okay, but these two pieces of steel, these coupon holders, were identical, and they were put in fresh pond water, just with two different phosphonate-style corrosion inhibitors. And you can see the effect of just, again, fresh water after 3 weeks sitting there stagnant at room temperature. Okay, so you can think that if you frack with the phosphonate scale inhibitor, what the inside of your downhole tubulars can look like after a short period of time. Well, that slide turned out, but anyways, again, just additional corrosion tests with different, and again, when you're looking at corrosion inhibition chemistry for high salinity brine and oxygen, you look at the literature from just about any company's products where they talk about the corrosion inhibitor that's effective in the presence of oxygen and high salinity brine, it will inevitably have either some type of phosphonate chemistry in there. There's several different types of phosphonates, and each one of them is got varying degrees of corrosion inhibition capabilities under certain conditions. But from a standpoint of functionality, low dose rate, and economics, that phosphonate chemistry is typically what is primarily used in these situations. There are some newer chemistries which are more polymeric based, and that is what's been used in some of these tests here, and that is added to the corrosion inhibition potential of these products. So on the left here, so this was 120,000 TDS brine. So the left two coupons, which show reasonable amounts of corrosion after just 1 week. The middle coupon, which had a measured weight loss corrosion of 0.5 mpy after submersion in that fluid for 1 year. And the right two coupons, which are heavily corroded, or other inhibited solutions, but after about half a year. So again, you can see quite a dramatic difference between what different chemistries' effect can be from an inhibition standpoint, or lack of inhibition standpoint thereof. This was a test I had done when a customer said they were encountering some coil tubing failures on a regular basis, and also coils were not cheap. And so running some tests, and you can see the conditions there, just 48 hours, 2% potassium chloride. I said the temperature ranged from 70 to 90. That was because the pumps I was using to recirculate the water, I had two pumps and I was switching them back and forth. One of the pumps generated more heat than the other did, so I tried to even out the amount of time. So that was the temperature range, and again, not very hot for the most part, but still a substantial amount of corrosion product occurring within 48 hours. The metal corrosion loss in the comparison between the inhibited coil, that corrosion was arrested by about 96%. This was on a drilling mud, about 25% sodium chloride, so fairly corrosive. 90 degrees C, so again, higher temperature, elevating the corrosion rate. pH of 10, so a little bit lower on the pH corrosion curve, but still very corrosive fluid. The customer that had asked for a solution in this case had quoted that they were experiencing 6 to 8 pounds of metal loss per foot per year on their drill strings. And that was with using a traditional amine inhibitor. So again, on this test here with more of a polymer type phosphonate blend, you can see that we got the corrosion rate down to 0.43 MP1. So the effect of oxygen, the effect of high salinity brine, very dramatic, but they can be controlled. And so just to summarize, again, fracking and many other applications here, like the drill outs, etc., drilling, we are going to be using high salinity fluids, oxygenated fluids. And so knowing how to, if we want to really extend the lifetime of the metallurgy that comprises these systems, the thinking needs to change a little bit of what else can we put in here that is going to make our lives easier down the road. Vince and I have already had several discussions about customers that have come to him at RJ Lee, showing them corroded pipe and corroded production tubulars and having all sorts of corrosion problems on their production side. And I personally think that these are largely not 100% preventable, but we could actually reduce their effect dramatically if we approach things differently from the front end. I'm very in tune with the cost of disposing of water in this area, and I doubt that's going to change anytime soon. So water reuse and water recycling is only going to increase in this area. So having chemistry again that can minimize the corrosiveness of that high salinity brine is going to be very important, again, to protect the integrity of your well and of your transfer lines. There's still some advances, I believe, that need to be made, but there are some interesting improvements, and some companies, some manufacturers that are working on chemistries to make better corrosion inhibitors for these conditions, for high oxygen, high salinity brines, calcium compatible, high temperature compatible, etc. So there's still some way to go, but I think right now some very good results are being achieved. It's just a different way of thinking, away from the traditional amine and quad type chemistry to more polymer and phosphonate type chemistry. Another comment here as to what I was mentioning about my discussions with Vince is that the more we can treat things proactively or preventatively, the more that we will have better results on the outcome side. So if we do our jobs a little bit better at the stimulation side or the coil tubing drill out side, the drilling side, the chances are is that when these wells are on ultimate production, we won't have as many problems to deal with related to corrosion. And again, just a comment for once we get to a lot more recycling and reuse operations, there's going to be more of these high salinity oxygenated fluids flowing through pipelines, held in storage tanks, etc. Having this approach where we inhibit these fluids is just going to save us a lot of problems. And I mean, I'll touch on one last thing, and I'm sure any of you who have worked on the friction reduction side of fracking are very well aware. It's probably hard to find a single ionic species in brine that kills an FR more than dissolved iron. And so by doing this, by keeping that iron on the pipe wall wherever we possibly can, we are going to allow that friction reducer to do its job and not deprogram it to like what the friction reducer wants to be, because originally when the friction reducer grew up, it was an anionic flocculant. We just kind of changed the game a little bit and said, no, we don't want you to flock anything, we want you to reduce friction. But having something like iron in there will cause major issues on your stimulation side. So there's multiple benefits for taking this proactive approach and dealing with the oxygenated and high PDS fluids. So something that I've always I've recommended it for the last few years, and again, I'm sure you companies like RJ Lee, as they start to see more issues from their customers on the production side, will start to follow suit as well. All right, thank you.